Hello everyone. In our previous simulation, we focused on the mixing behavior between ethanol and water within a stir tank. During that setup, we carefully prepared the geometry and create the quality mesh, which helped us visualize the mixing pattern using the CFD tools inside the ANSYS Fluent. The tutorial provides us with a clear understanding of how fluid properties and impeller motion affects the distribution of the components over the time. Now, in this new simulation, we are taking things a step further. Rather than simulating a simple mixing, we are now introducing a chemical reaction mechanism into the systems. And our goal is to study how the impeller speed and the mixing intensity influence not just the blending of the fluids, but also the reaction yield and the conversion rate. We will analyze how different impeller rotation speeds starting from 10 radians per second and increasing to 25 radians per second and impact the progress of the reaction and the production of the desired chemical species. Let's start with preparing our setup, and the solver will be pressure based, and velocity formation will be absolute, and the time will be transient, and the gravity will be in the z direction and minus 9.8. What is necessary to do at the first is to introduce and define our reactant. In this simulation, we investigate the effect of the mixing intensity on the reaction yield inside the stir tank reactor. The reactor contains two reactants, sodium thiosulfate and hydrogen peroxide. The efficiency of this reaction is strongly influenced by how well the two reactants are mixed, which is directly related to the impeller speed. Let's follow the simulation setup. We approach this problem using, as you see, computational fluid dynamic. And for the first, I'm going to modeling the both fluid flow and species transport with the volumetric reaction. And we will simulate it two scenarios. Case 1, low mixing speed 10 radian per second. And the second scenario will be high mixing speed with the 25 radian per second. Let's start with defining our material. And from the fluid, I've defined this before. And I'm just going to show you how to define the properties inside ANSYS Fluent. We start with the Fluent database. You can easily find your material and your component from the Fluent database. If it doesn't exist, you can easily add your properties and you can create your desired component. And for example, if you want to introduce hydrogen peroxide from the fluid, you will come and you will select hydrogen peroxide, hydrogen sulfate, and hydrogen peroxide, and you will click on copy, and the component will be added on your list. I've done this before, I just want to simply show you how to add the materials into your list. So I have added hydrogen peroxide and this and the sodium sulfate and the sulfur water liquid. And then after you did this, you will come to turn on the species transport. And turn on the species transport, and the reaction will be volumetric. And the chemistry solver, you can select your chemistry solver like the chemical equilibrium or direct sources. And what's the next is to define your species into the mixture. So my reaction species is this. And these are the product, sulfur and the water liquid, and this. Well, when I have added all the component, and I will click on OK. Then I'm going to define my reaction. Well, I have just one reaction. It's irreversible reaction. And we need to define our Arrhenius rate for kinetic of the reaction, and this is this number, and the activation energy is this number. Well, our reaction contains two reactant, and this is the first species, and this is the second species as a reactants. Well, the stoichiometric coefficient for first is the 1, and for the hydrogen peroxide is the 2. And this is our product, and species, sulfur, and water liquid. And the stoichiometric coefficient is 1. And pay attention, the reaction type will be volumetric. And then you can click on OK. Well, afterwards, the things you need to do is to select your density. And I've selected the volume weighted mixing law and specific heat with the mixing law, and thermal conductivity, mass weighted mixing law, and viscosity and the mass diffusivity. Then when you have done this, you should click on change. And everything is okay. All right. And what's the next? The next is to define your impeller rotation speed. So we have a batch system. We have an inlet and outlet and the steady state condition, but the component exists from scratch, and we need to define our impeller rotation speed from the cell zone condition and from the inner part and the shaft. And from the inner part, for the first simulation, I've done it, and then I got the results. I will show and compromise these two results according to the mole fraction of product. So you will see how impeller affects on the yield of the products. Well, for the first, I've simulated with the 10 radian per second, and for the second simulation, I've run with the 25 radian per second. And pay attention, this option will be frame motion, because we didn't create mesh motion, and we are just gonna working with the frame motion. And the reaction is this option you can use, and other things if you want to add it for your simulation, like the UDs for your cell zone condition. You can turn on the source term, and on the source term you can add your user defined function here, and click and apply. And for the shaft we will do the same, and the speed is 21, and the frame motion and everything is okay, and click and apply. For the boundary condition, we haven't inlet and outlet, and we are not just gonna adjust our boundary condition. And another thing I forgot to tell you, we should select our viscous model, and I've selected K₂O₃ equation model as a template one. And in the computational fluid dynamic simulation, particularly involves the stir tanks with the chemical reaction, turbulent viscosity plays an important role in defining how momentum, species, and energy are transported throughout the fluid domain. And when you're using the fluent, turbulent viscosity is not something we manually assign. Instead, it's dynamically calculated by the turbulence model selected, such as widely used K epsilon and K₂O₃, or other Reynolds average Navier-Stokes runs model. As I said, I use the K₂O₃ here. And the turbulent viscosity essentially represent the effect of the turbulence on the fluid's effective viscosity. Well, in the real flows, especially in a system like stir tanks, there is a wide range of the eddy size, from large impeller driving vortices to smaller turbulent fluctuations. Well, these eddies act like additional mixing mechanism beyond what molecular diffusion and momentum transport can achieve. Well, Fluent can capture these effects by computing an effective viscosity, which is the sum of the molecular viscosity and the turbulent viscosity. This effective viscosity is then used in the governing equation for momentum, species transport, and energy. Well, then click on OK. Well, for methods, I will use the simple and gradient less square cell based, and the pressure presto, and momentum quick, and the rest as you see in the screen. Well, for the controls, it's the under relaxation factors, and I didn't adjust this. And if you have a convergence problem, and you can adjust and decrease these numbers. And for initialization, I've initialized with this. And the more important thing that is this, have to define our fraction of our component inside the stir tank. So we will use the patch, and you will assign a region for your stir tank with the adapt option here, automatic, and the cell registration, and you will create the new region. And from which part of your tank you want to assign your component, you can easily select points there, and you can add your component exactly to that area. And the region will be appeared in initialization and the patch section. And I've created this region, and the value, the first value for hydrogen peroxide for the region, I selected the 1, and for this reactant, I've selected the value 1 for region 1 and in part of the tank. Then I've clicked on the patch, and this ways can easily say that this component is exactly exists from scratch, and this is the batch system, and then close. And what's the next to do is to click on run calculation, and I run for 30 seconds of the transient system simulation, and with the time step 0.1. So if you want to get the exact and reliable report, you should increase your time step size to 10 power minus 3 or even 10 minus 2. But in order to decrease the computational time and get to show you how to mixing, increase the mass transfer and also the yield, I just simply set this 0.1. Then when you click and apply, you will see that the effect of Impeller and the yield of the production system. Well, after running the simulation, let's compromise our simulation results. Well, please be sure that all your component converge properly, and everything is okay. I just want to show you how sodium sulfate increase with increasing the Impeller speed. Well, this is the result of a 25 radian per second of the Impeller speed, and we get this number as you see here. And this is the Impeller speed with the 10 radian per second. As you see, it's around 0.28 and 29. And this at the higher Impeller speed, turbulence increase, and this leads to smaller eddies and the higher mixing frequency and faster homogenization of the species. Well, actually, this enhanced turbulence reduces the concentration gradients and ensure that the reactants are brought into contact more frequently and uniformly throughout the reactor. As a result, mass transfer resistance decreases, and especially important in the reactions where the mixing rate is comparable to or slower than the chemical reaction rate. I've used a finite rate chemistry model, possibly combined with the turbulence chemistry interactions. And in a such model, mixing directly influences the rate at which reactants meet and react. With the more efficient mixing at 25 radian per second, the reaction proceeds faster and more uniformly, and explaining the increase in the product formation. And this is the water production, as you see in the 25, and it's different with the production with the 10 radian per second. And the hydrodynamic uniformity, the impeller motion creates the circulation loops and the vortex structures with the higher rotation, and the follow patterns are quite stronger, and the dead zones also are minimized. This ensures that all the region of the tank are involved in the reaction and improving overall performance. Well, in the conclusion, if you want to discuss with the conclusion, this simulation confirms that the impeller speed has a direct and significant effect on the reaction yield and the mixing sensitive system. The higher yield at the 25 radian per second is both theoretically expected and numerically validated by the simulation results. It's illustrates the importance of the hydrodynamic in optimizing reactor performance. So, also, if you want, you can easily see your turbulence, kinetic rate of the reaction, and from which area of the stir tank we have a more turbulence. Let me know what kind of simulation do you want to simulate, and write your idea and write your perspective under the captions. Thank you for watching this video, and let's see you with the different tutorials.